Section. Introduction. We begin with a quote from Richard P. Feynman. "What I cannot create, I do not understand." This statement emphasizes the importance of creation, or synthesis, as a high form of learning. Unlike simply analyzing a text or image, creating something from scratch requires a deep understanding of the underlying factors and processes involved. This is true whether you're learning a new language, solving a math problem, cooking a meal, writing a novel, or creating a work of art. In the field of artificial intelligence, we've seen significant advancements in generative models, which can create highly detailed and realistic images. However, most research has focused on using these models for synthesis or editing, with little attention given to their potential for representation learning. We believe that these models, which can create such detailed images, must also learn a lot about the properties and processes that make up these images. So, how can we harness this potential for representation learning and use it to benefit other tasks? To address this question, we introduce SODA, a self-supervised model designed for both perception and synthesis. SODA combines an image encoder with a classic decoder, both trained together for novel view generation. The encoder transforms an input view into a concise latent representation, which then guides the denoising of an output view by modulating the decoder's activations. This setup creates a desirable information bottleneck between the encoder and the decoder, providing our model with an explicit and interpretable visual latent space. Our experiments show that this approach has two main advantages. First, it encourages the development of disentangled and informative representations that capture key image properties and semantics, which can be applied to other tasks. Second, it provides effective means to control and manipulate the produced outputs, benefiting image editing and synthesis. We've also incorporated several new ideas into the network architecture and training procedure to maximize its representation skills. We demonstrate SODA's strengths and versatility by evaluating it on a series of classification, reconstruction, and synthesis tasks, using a wide range of datasets that cover both simulated and real-world scenarios. SODA performs well in linear probing experiments over the ImageNet dataset, among others. It also excels at few-shot novel view generation and can flexibly synthesize images either conditionally or unconditionally. We also found that the model's latent space has a disentangled nature, which offers control over the semantic traits of the images it produces. In summary, SODA integrates three research ideas that we aim to promote. 1. Models are not only good at image generation, but can also learn strong representations. 2. Novel view synthesis can be a powerful self-supervised objective for model pre-training. 3. The compactness of the latent space, achieved by constricting the neck between the encoder and the denoiser, plays a crucial role in enhancing the quality, informativeness, and interpretability of the latent representations. We also discuss related work in the field of visual synthesis, visual encoding, hybrid models, and downstream tasks. We compare SODA to leading prior works in each of these areas, demonstrating its versatility in tackling both representational and generative tasks. Section Summary. In this section, the authors introduce the concept of synthesis as a high-level manifestation of learning, where creating something requires a deep understanding of the underlying factors and generative processes. They propose SODA, a self-supervised model that combines perception and synthesis by using an image encoder and decoder to generate novel views. The model's advantages include the emergence of disentangled and informative representations, control over the produced outputs, and a compact and interpretable visual latent space. The authors demonstrate the model's strengths in various tasks and highlight the importance of representation learning and the effectiveness of self-supervised pre-training. Section. Approach. Our approach involves a self-supervised model called SODA, which learns to map images and their latent representations in both directions. This model includes an image encoder that transforms an input image into a low-dimensional latent representation. This latent representation then guides the creation of a new output image that is related to the input image. SODA's design provides it with a clear and compact latent space. This not only gives us a lot of control over the image generation process, but it can also be used for other perception tasks. We'll first give an overview of the model, then delve into the details of its main components, the design of the encoder, the mechanisms used to create new views, and the optimization techniques we use to develop strong and meaningful representations. SODA is a denoising model, which means it's defined by a pair of forward and backward Markov chains. These chains iteratively transform a sample from a normal distribution into the target distribution and vice versa. Each forward step adds a small amount of Gaussian noise to the sample, while each backward step aims to estimate this noise in order to recover the original sample from its noisy version. This backward step is performed by a decoder, which is a type of convolutional neural network. To help the decoder with the denoising task, we condition it on a latent vector. This vector guides the decoder's operation by adjusting the activations at each of its layers through adaptive group normalization. This normalization controls the scale and bias of the activations. The latent vector is created by a new image encoder, which we'll discuss next. This latent representation is at the heart of the model, serving as the communication channel between the encoder and the denoising decoder, and guiding the latter through the process. It's created by a ResNet encoder, which represents a clean source image that is semantically or visually related to the target image. The motivation behind this idea comes from the inherent uncertainty in the denoising task. The decoder will use any relevant knowledge or useful hint that could inform it of the missing content to fill in. This encourages the encoder to distill the most striking and prominent similarities between the source and target images into the latent representation. Since we further constrain the latent representation into a low-dimensional space and use it to guide the decoder, it encourages the latent representation to specifically capture the high-level semantics of the image, while leaving the reconstruction of localized and high-frequency details to the denoiser. From this perspective, learning a latent representation that supports image denoising, rather than pure reconstruction from scratch, allows our encoder to focus on the image's most distinctive and descriptive qualities. Section Summary. The SOTA model is a self-supervised model that learns a bidirectional mapping between images and latent representations. It consists of an image encoder that converts an input image into a low-dimensional latent representation, which is then used to guide the synthesis of a new output image. This design allows for control over the generative process and enables the use of the latent space for downstream perception tasks. The model is defined by a pair of forward and backward Markov chains that transform a sample from a normal distribution into a target distribution and vice versa, with the encoder serving as the communication channel between the two. Section. Layer modulation and masking. We're introducing two intertwined mechanisms to improve the disentanglement of our model's latent space: layer modulation and masking. In layer modulation, we divide the latent vector, Z, into m+1 sections, which is half the number of layers in the decoder. Each section of Z, denoted as Z_I, is used to modulate a pair of layers, H_I and H_2mi. This encourages each sub-vector of Z to specialize in capturing different visual traits at varying levels of detail, guiding the decoder's operation through the layers. To further enhance the model, we introduce layer masking. This is a layer-wise generalization of guidance without dependencies. During training, we randomly zero out a subset of Z from 1 to m. This acts as a layer-wise guidance dropout, reducing the decoder's reliance on sub-vector dependencies and allowing them to specialize independently. When sampling, we extrapolate the model's output in the conditional direction, which is the difference between the model's output given x_t and z, and the model's output given x_t and 0. This gives our model, SOTA, more control over the generative process and allows for image editing and style mixing. We can selectively condition the decoder on some levels of detail, like structure or position, while allowing it to freely vary others, like lighting, texture, or color. We also consider views, which are sets of images that share some relation, such as visual or semantic. These can be various augmentations or distortions of an original image, images of a 3D object from different angles, or images that share the same semantic category. We allow for the case where all views are identical, which turns the model into an autoencoder. Alternatively, we can create a novel view based on a set of k input views, instead of just one. The model can also incorporate richer forms of conditional information, like the camera perspective associated with each view. For 3D datasets like ShapeNet, we combine a grid of ray positions and directions, R, with the linearly mapped RGB channels of the source and denoised views, X and X_t. This allows us to generate novel views that match the requested pose and orientation. We extend guidance without dependencies for novel view synthesis, and randomly and independently mask either the latent or the pose information, R. This not only improves the model's generative skills, but also allows SOTA to generate novel objects at a requested pose, or generate novel views of given objects based on an image only, in the absence of source or target positional information. Finally, we explore the integration of cross-attention to support spatial modulation. Instead of layer-wise modulation, we divide the latent vector, Z, into n subvectors and perform cross-attention between the subvectors set and the decoder's activations. We find that cross-attention helps the model with 3D novel view synthesis, while layer modulation is better for image editing, reconstruction, and representation learning. Section Summary. To enhance the disentanglement of the model's latent space, we introduce layer modulation and masking. Layer modulation partitions the latent vector into sections and uses each section to modulate specific pairs of decoder layers, promoting specialization among the latent subvectors. Layer masking reduces correlations among the subvectors by zeroing out a random subset during training, allowing them to specialize independently. These mechanisms improve the model's control over the generative process and enable image editing and style mixing. Additionally, we explore novel view generation by considering sets of related images and incorporating richer conditional information, such as camera perspective and pose. Section: Training and Sampling. We're training our model using the standard mean squared error (MSE) objective, but we're introducing a new noise schedule to better suit the task of learning representations. Typically, models set the variance of the additive noise term, represented by the Greek letter epsilon, to follow either a cosine, sigmoid, or linear decay schedules. These schedules prioritize noise levels that are close to the margins, either at the high or low ends. While these schedules have been found useful for image synthesis, they don't work as well for representation learning. If the noise level is too low, the task isn't challenging enough for the denoiser, which reduces the necessity of the encoder. On the other hand, if the noise level is too high, it puts too much pressure on the latent variable, represented by the letter Z, to capture every pixel-level detail of the image, turning denoising into mere reconstruction. To address this, we're introducing a new inverted noise schedule that promotes medium noise levels instead of the extremes. This has proven to be highly beneficial for the quality of the representations. We've also made two modifications that we found beneficial for representation learning. 1. Adding low Gaussian noise to the input images of the encoder. 2. Optionally setting the encoder to have a higher learning rate than the decoder, which positively impacts their learning dynamics by allowing the encoder to adapt faster as it guides the decoder in the denoising task. Once trained, we use DDPM for sampling. We've evaluated our model, SOTA, through a series of quantitative and qualitative experiments, demonstrating its strong representation skills and generative capabilities over 12 different datasets grouped into 4 tasks. We start with linear probe classification, showing the model's utility for downstream perception. We then move on to image reconstruction and few-shot novel view synthesis, illustrating its ability to envision 3D objects from new unseen perspectives. We also explore the model's disentanglement and controllability, as substantiated by comparative analysis and latent space interpolations. We've provided additional samples, visualizations, and animations on our website, along with further details about our evaluation procedures, discussing the datasets, metrics, baselines, and implementation details. We conclude with ablation studies that empirically validate the contribution of the model's components and design choices. In our linear probe classification, we assess the quality of SOTA's learned representations over ImageNet and Celeba. The former requires fine-grained clustering into 1,000 possible categories, while the latter involves rich identification of diverse semantic attributes. We train our model in a self-supervised fashion, using RAND augment for ImageNet and Gaussian data augmentation for Celeba. We then fit a linear model over the latent vectors, represented by the letter Z, that predicts the category or attributes, and measure the resulting performance. As shown in our results, SOTA reaches 72.24% accuracy on the ImageNet 1K linear probe classification task, outperforming competing generative approaches such as MAE, BAIT, and IGPT, and significantly reducing the gap with discriminative and contrastive approaches like DINO, SWAV, and SIM-CLR. For Celeba, our model achieves the strongest results compared to competing approaches. SOTA proves remarkably robust to the choice of data augmentation, performing strongly regardless of the selected strategy. The newly introduced image encoder plays a crucial role in the model's downstream performance, enabling a significant boost over features obtained from an unconditional model. A significant improvement also comes from the use of novel view synthesis as a self-supervised representation learning objective. Other contributors include the compact neck and feature modulation, which respectively raise accuracy for ImageNet and F1 for Celeba. Designing a new inverted noise schedule that favors medium noise levels in lieu of the extremes also strengthens the model's representation capacity, leading to an increase over ImageNet. Section Summary. The paper introduces a new noise schedule for training a model that improves representation learning. The schedule promotes medium noise levels instead of extreme levels, which enhances the model's ability to capture details without compromising the denoising task. The model, called SOTA, demonstrates strong representation skills and generative capabilities across various tasks, including linear probe classification, image reconstruction, few-shot novel view synthesis, and disentanglement and controllability. It outperforms competing approaches in terms of accuracy and robustness to data augmentation. Section: Visual Synthesis. We're now going to delve into the generative capabilities of our model, assessing how well it can recreate an image from its latent encoding and generate new views of 3D objects from given camera perspectives. We'll be looking at how similar the model's predictions are to the target images in terms of pixel structure, overall image structure, perceptual quality, and semantic content. When it comes to image reconstruction, our model, SOTA, outperforms other models like VQGAN, StyleGAN2, DALL-E, and Unclip. Our images are sharper and more accurate, possibly because these other models don't have a trainable encoder. What's impressive is that we achieve these results with a much lower dimensionality of the latent encodings from which we restore the images. For instance, SOTA uses 2K dimensions, while VQGAN and DALL-E use between 65K and 524K. This shows the advantage of continuous representations over discrete codebooks. Next, we tested SOTA's ability to generate new views of 3D objects, using 3 datasets that include both synthetic object renderings and real-world scans of household items. We compared SOTA to other models, some of which are geometry-free and some of which are geometry-aware. We found that SOTA consistently outperformed the other models across all datasets and for different numbers of source views. SOTA was particularly good at producing sharper images that better matched the source views both structurally and semantically. We noticed that SOTA performed best when given 1 to 3 source views. For the single source case, it improved the perceptual quality scores by an order of magnitude and often almost halved the semantic content scores. We also found that our proposed view aggregation method outperforms the stochastic conditioning technique of 3DIM. Our approach also outperforms the denoiser-only palette model, which is good at tasks that closely follow the source layout, like colorization or super resolution, but struggles at structural transformations. The concept of disentanglement has been a recurring theme in representation learning research. The goal is to discover abstract and meaningful latent representations that align with the natural axes of variation. Disentanglement could enhance the encoding's interpretability and, in the context of generative modeling, support greater controllability. We inspected the model's latent space and analyzed it along the dimensions of disentanglement, controllability, and informativeness. We visualized latent interpolations for our model, linearly traversing the latent space from one vector to another. We observed smooth variations over traits of texture and structure. We also identified meaningful latent directions that correspond to individual axes of variation. We found that these manipulations are disentangled. One attribute is altered while the others are mostly kept intact, demonstrating the well-behaved nature of SOTA's emergent latent space and the quality and strength of its learned representations. We also investigated the effect of layer modulation and masking, blocking the encoder's guidance from select decoder's layers and inspecting the impact on the produced outputs. This allows for selective modification of input images at different levels of granularity, so to preserve certain factors while unconditionally regenerating other ones. We found that layer masking improves the model's robustness to these forms of partial conditioning. The role played by the initial Gaussian noise map is closely linked to the chosen augmentation scheme. It controls fine stochastic subtleties like fur or freckles when SOTA is trained to reconstruct the source image, and could conversely shape the underlying layout when heavier data augmentations are applied. Section Summary. The model's generative skills are evaluated by assessing its ability to reconstruct images from their latent encoding and generate new views of 3D objects based on requested camera perspectives. The results show that the model outperforms competing approaches in terms of image reconstruction quality and novel view generation, producing sharper and more accurate images. Additionally, the model demonstrates disentanglement and controllability in its latent space, allowing for smooth variations and attribute manipulations that influence various semantic properties of the generated images. Section: Quantitative Evaluation. Quantitative Assessment. To further support our previous findings, we conducted a detailed analysis of our method using the DCI metric. This metric evaluates the quality of representations based on 3 criteria: disentanglement, completeness, and informativeness. It does this by checking how well the latent factors correspond to the actual factors of variation. See Appendix E.3 for more details. We tested our models on several datasets that have semantic annotations. These datasets range from the simpler ones like small norb and MPI3D to more complex and realistic ones like cub and celeba. As shown in the table labeled tab_Dyson, and in supplementary tables 6 and 7, our method, SODA, performs better than both variational and adversarial methods. It improves disentanglement by 27.2% to 58.3% and completeness by 5.0% to 23.8% across 4 different datasets. The only exception is the synthetic 3D shapes dataset, where SODA and most variational methods already achieve excellent results. When it comes to informativeness, the results are mostly similar. SODA leads in some datasets, while other methods like StyleGAN or DipVAE perform better in others. Our experiments also show that layer modulation and masking contribute significantly to the performance of our method. They lead to an increase of 3.2% to 13.5% and 2.5% to 8.9% in disentanglement in the latent space, and an average increase of 3.8% and 1.7% in completeness, respectively. Visually, the samples generated by SODA are noticeably clearer than those produced by variational methods. Moreover, SODA significantly improves the realism, as measured by the FID score, and the semantic similarity, as measured by the LPIPS score, of the generated samples.